about calculating flux. All right. So, anybody? Did we talk about flux capacitors? Yeah. Oh, I got an email. Cragen has a flux capacitor listed on their website. It's actually not the first time I've seen that, but it is still pretty fun. It's always out of stock for some reason. So we're going to talk about calculating flux. So we're first going to say, okay, this is a rectangle. Everybody believe me?
Yes.
Okay, we're looking at it from the side. We define the vector. Well, we'll talk about the area vector later, but here's a vector normal to the rectangle. Okay. Here's another rectangle, now it's on the side. Here's a vector normal to the rectangle, okay? Now we're going to put a vector field in this rectangle. So here's our vector field. It's just a bunch of arrows, okay? So our vector field is pointing in the direction of the normal vector, okay? So that means the vector field is parallel to the normal vector, all right? Here, what about here? Vector field is perpendicular to the normal vector. So these vectors can be anything, but let's say that they're air particles, the speed of air particles, okay? So this thing is a little bubble one. So it's not a rectangle, but it's a surface, okay? It's a shape. Here's the surface. It's got a surface area of about pi r squared, all right? So if I create a vector field perpendicular to that surface or parallel to the normal vector of that surface, what happens? Nothing. Not very dramatic. Okay? So you get pretty nice big bubbles. What if I turn this thing perpendicular? So if I make the velocity vectors of the air perpendicular to the normal vector of the surface. Not a lot happens. Okay? So this is this situation. Alright? This is the maximum flux. So when the vector field is parallel to the normal vector of the surface, that is maximum flux, okay? This is minimum flux. When the vector field is perpendicular to the vector normal to the surface, right, you have zero flux. Haha. All right. So in this case, we're saying this is the volume of air per second that flows through the loop. So here, this is the area of the loop, A, all right? We multiply that by the speed of the air, v. But what happens if I turn this slightly sideways? Right, so here, it's just v times a. Here, it's 0. But what if I just put it at an angle?
V times a times cosine.
So what happened to the bubbles? Yeah, because what happened to the bubbles?
They got smaller.
So these are pretty big bubbles, right? Bubbles are a little bit smaller, okay? Why?
There's a less like surface area.
There's less surface area visible to the vector field going through it, okay? Because when you look at this thing, so if you look at a circle and you're perpendicular to the circle, you see a circle. If I tilt it, what do you see?
Oval.
An oval, okay? And if I tilt it more, you don't see any of the circle, okay? So when you want to describe this mathematically, the way that you do this is you take the dot product normal to this area, right? So you take the area normal vector, you multiply that by the area, and you take the dot product of that vector and the vector field, okay? So that's going to give you cosine theta, all right? So the flux, the volume of air per second that goes through, right? The amount of stuff that goes through the area is going to be the vector field value times the area cosine theta, which is a dot product, okay? And that's going to give us the thing that what we observed, right? When our normal vectors are parallel to the vector field, when the normal vector of the area is parallel to the vector field, you get a maximum. When it's perpendicular to the vector field, you get 0. And anywhere in between, you get whatever your vector field is times area cosine theta. So we're going to do this not for airflow, but for electric field vectors. All right, so our electric field vectors say, here's our area. If we have an electric field going through this area at an angle theta, then this is the flux, okay? But this is for what kind of electric field? It's going to have to be for constant electric field, okay? And how many of these electric fields are constant? Just this one. Okay. We're going to have a little bit different technique if we're talking about non-constant electric fields. But just for now, for a constant electric field, just to introduce flux, flux is the field vector as a dot product of the area. Okay? If you want to write this in non-vector math, it's electric field times area cosine theta. Okay? So remember, so let's define the area vector. The area vector is the area, so if this is a circle, it's pi r squared, and it points in the direction normal to the surface. Okay, so the area vector is always perpendicular to the actual area. Okay, so it's perpendicular to the surface. Units of flux are not great units. This class doesn't have the best units. They're Newton coulombs times meter squared. I apologize for the units of flux. But yeah, Newton's meters divided by coulombs. Newton meter squared divided by coulombs. So, that's that. All right? Any questions about this? Cool. Any question? Now that you know what a flux is.
Or for the road.
So, what's cosine theta here?
1.
1, right? The vectors point this way. The vector normal to the surface is also this way. So that's going to give you 1. All right? What's the electric field? Well, it's constant. Okay, it's the same electric field here as it is over there. So what's the only difference between these two things? Area. And you can put a circle in a square and still have some square left over. Okay? So that means the area of the square should be bigger than the area of the circle, which means the flux through the square is bigger. Yes?
So what if it was like a sphere in a circle?
A sphere?
Yeah, in a circle.
Sphere?
Oh, never mind. Sorry, you said something about surface area.
Yeah, so, okay, well, actually, we will get there. But, well, let's not skip ahead, all right? So, let's calculate the electric flux, okay? So here, when we're actually calculating Gauss's law, it has to be a closed surface, okay? So here, when electric field points out of a surface, that means the flux is going to be positive, okay? And flux, what's this letter? Phi. It's phi, but it's capital Phi, okay? So it's capital Phi, yeah, we have our Greek alphabet up here. Capital Phi, lowercase phi. So this one's like an angle for like spherical coordinates, and this one's flux. Okay? And we call it flux sub E. What does the E stand for? Electric. It's the electric flux. Why do we call it electric flux? What other flux do you think we're going to have in this class? Magnetic, because this class is electricity and magnetism. So, yeah, it's very complicated. Okay, so when electric field points out of a surface, the flux is positive. When it points into the surface, it's negative, okay? And that's because, remember, the normal vector points away from the surface, but the only way you really know the direction of the normal vector is if it's a closed surface, right? If it's a closed surface, the normal vector points out on the outside of the surface, so you have to compare it to that vector. If you just got like a plane, then it's not really clear if the normal vector is up or down, okay? But the normal vector, when we're doing these problems with a closed surface, always points out from the surface. So that means when the electric field is parallel to the normal vector, meaning it's pointing out like this, what sign is the flux? Positive. Okay? What about this? That would be negative. Okay? What about this? Positive. What about this?
No. Oh, wait, you can't have negative. It's 0. It's equal to 0.
Zero flux. Okay? So if you have the same number of electric field vectors going in as you have coming out, that means you have no flux. Okay? So I want you to think about this. So let's talk about divergence. Remember, we talked about this the first day. So this Gauss's law stuff comes from something called the divergence theorem. And anybody remember what divergence looks like mathematically? Yes.
When you're going to infinity, or when you're taking something to a certain place, it goes to infinity.
that's not what we're talking about. So vectors, right? Let's say we're talking about the electric field vector. Let's say we want to take a derivative of the electric field vector. Okay? What are ways you can take a derivative of a vector? So what's a vector, three-dimensional vector derivative look like? What's the shape? Looks like this. Okay. So this is a vector derivative. If you want to write out what it looks like, let's say in Cartesian coordinates, it's dx in the x direction plus dy in the y direction plus, well, this is actually del z in the z direction. So it's a partial derivative in the x direction, a partial derivative of y in the y direction, partial derivative of z in the z direction. Okay? There's two ways to use this. What are the two ways you can multiply vectors? Dot product and cross product. Okay, we're not going to deal with this one right now, but I just want you to know that it's still a possibility. Okay, this is the divergence theorem, sort of. It's part of the divergence theorem. Okay, this is divergence. So this is measuring the divergence of the electric field. Okay, and the electric field is a vector field. So what do we mean by divergence? Well, let's think about an air-filled balloon. Okay, so if we choose the vector field to be all the vectors of the air molecules, let's say their velocities. Okay, so figure the velocities of the air molecules. You have this balloon. If you heat up the balloon, what happens to the net of that vector field? What does it do? Which way does it point? Outward. What happens to the balloon? It's bigger. Okay, you heat up the air all starts moving faster, but the net is going to go out. Okay, but if you cool it down, it goes in and gets smaller. Okay, so the net vector field, when you sum up all the vectors in the vector field, on average they point in. Okay, this is called divergence. So if the vectors start to point out, right? You have net vectors pointing out, that's positive divergence. If it's pointing in, that's negative divergence. If for some reason they're neutral, right, that's zero divergence. Okay? So basically, anytime you have a source where lines, vector field lines come out of it, you're going to have a divergence or come in. Okay? So the case where you have the positive charge inside the Gaussian surface and the negative charge inside the Gaussian surface, where all your vector lines point in or out, that's a non-zero divergence. The case where all the lines go straight through, what's the divergence there? Zero. Okay? So this just measures whether something has a source, right? Whether your vector field starts and ends someplace. Okay, that's what the divergence measures. And so you don't have to know this, but this is where this whole concept comes from. So this sort of measures the flux. Okay? It's not quite the flux, but it's sort of getting towards the flux. It's the hand-wavy flux. Yeah. Okay. So let's try something out. And we'll do this one together.
Okay, so let's talk flux. So we have 200 centimeter squared parallel electrodes spaced 2 centimeters apart. And I just want to point out that when you see something like this, what they're really saying is this is a capacitor. And you can tell this even more because one is charged to a positive charge, and the other one is charged to a negative charge, and those are equal charges. So this is not just a capacitor, but a parallel plate capacitor. And we'll talk more about these when we get to capacitance, but remember, you can treat a capacitor essentially as an infinite sheet of charge, well, two infinite sheets of charge of opposite charge next to each other. And capacitors can get more complicated than that, but that's the simplest model, and it works pretty well for most cases. It's also a really good way to create a constant electric field. A parallel plate capacitor is the ideal way to create a constant electric field. Okay, so we have this parallel plate capacitor, and I'm going to draw that out, but first there's a surface between it, so basically just like a Gaussian surface, but not closed, so maybe not Gaussian, but like mathematically just an imaginary surface, and it makes a 45-degree angle with the electric field. And so we're going to draw this from the side. We're looking for the electric flux, right? That's the question. So we're going to start by drawing this parallel plate capacitor. So we have two parallel plates. On one side, we have positive charges, so plus charges. And so we'll call this plus Q. And we know this is plus Q. And then on the other side, we have negative charges. They should be equal. And this is negative Q. Okay, and this is our negative Q. All right. So we also know that this has an electric field that looks like this. So it goes from the positive to the negative. So that's our electric field. And then we're given that the spacing between this is going to be 2 centimeters. We also know that we have this object, this sort of square in between these two things that is at an angle of 45 degrees to the electric field. So this is a side view of it. Okay, and then the angle is 45 degrees. Okay, so this brings us back to our definition of flux. So the electric flux, which is this capital phi, is going to be E dot A, and we can write it this way because it's a constant electric field. When it's not a constant electric field, obviously you're going to have to use an integral. But in this case, we know this is a constant electric field because this is a parallel plate capacitor, which by definition has a constant electric field. Okay. The other thing we want to remember is this is a dot product. So you can also write this as EA cosine theta if you don't want to write it as in the vector form. So this is a fairly simple equation. So this is our equation for flux. And this is what we're trying out. So in order to figure this out, we need to figure out the electric field first, and then the area of the surface, okay? So the electric field is going to be the electric field for a parallel plate capacitor. So for a parallel plate capacitor, we know that the electric field for a parallel plate capacitor is eta over epsilon naught. Remember, eta is the surface charge density, right? Surface charge density. But since we don't actually have the surface charge density, we're given the charge in the area, we know surface charge density, as a side note, is Q over A. So we can rewrite this as Q over A epsilon naught. Okay. So this is a definition. We know this is the electric field of a parallel plate capacitor. Let me make that. And so we're just figuring this out from there. So we can plug in these values. We know that the charge, and we just use the positive charge here because it doesn't matter that there's two plates. You only use the charge of one plate. It's the density of the charge that's on both plates, since they should have an identical density. And you don't need the negative because we already know the direction that the electric field is going. It's going this way. So let's write 5 times 10 to the negative 9th coulombs over the area. This is 100 centimeters squared. Well, that's 100 centimeters squared. We need to convert that to meters squared. Okay, so that's going to be 100. So actually, just as a side note, if you want to go from centimeters to meters, if we have 1 meter, that's equal to 100 centimeters, okay, which you can also write as 10 to the 2 centimeters, okay. If you cube this, that means you have 1 meter cubed, and that's 10 to the 6th centimeters cubed, okay. So if you want to go from 100 centimeters cubed to 1 meter cubed, we know that for every meter cubed, we have 10 to the 6 centimeters cubed. So you can also write this as 10 to the negative 6 meters cubed is equal to 1 centimeter cubed. So we can write 100 times 10 to the negative 6 meters cubed, because we need this to be in meters cubed. And then we have 8.85 times 10 to the negative 12 Coulomb squared over Newton meter squared. Okay. And I'm going to move this over because it's kind of in the way. Okay. So this is a side note on conversion. And this gives us 5.65 times 10 to the 4th newtons per coulomb. Okay, so that's our electric field. We also need to figure out our area, and the area we're looking for is the area of this thing, which is actually this area. So this is this thing, okay? So the area, not the area of the parallel plate, it's the area of the thing in the field. So the area should be, it's 1 centimeter by 1 centimeter, so 0.01 meters squared, because it's a square. Okay, so this gives us 1 times 10 to the negative 4 meters squared. So if we want to calculate the flux, right, so here's our area, here's our electric field, right, so we need E and we need area. We want to take this and actually just plug in our values. So that's going to be and this, and then cosine 45 degrees, that's the angle between them, and this should give us 4.0 Newton meters squared over coulombs. which is our final answer. So just to recap, we calculated the electric field due to a parallel plate capacitor. Then we calculated the area. So the parallel plate, this part is the parallel plate capacitor, so that gives us the electric field. Then we calculated the area that the field is going through because we want the flux through this thing. And we also have to consider the angle because we know that this is a dot product. Okay. Okay, so here's another problem. I'd like you to take a look at this and try it yourself. And this one is a little bit different from the previous one. So remember, the normal vector points out of a surface. Even though we're only given one flat surface, they're giving you the normal vector so you know which way is out. And that should help you figure out what the sign should be. The electric field in this case, unlike the previous problem, is given to you. It's uniform. And it has a magnitude of 180 newtons per coulomb, and we're still trying to calculate the flux. We're given the flux equation again, so we need to find the electric field, the area, which is pretty much given to us, and then we mostly are in this problem, we're trying to deal with the angle, because remember, the electric field is given, it's E, and this is just the magnitude of it, 180 newtons per coulomb. The area is 0.15 meters, and this is a square. So that's 0.15 meters squared. And then we know that our flux is EA cosine theta. The only real tricky thing is that the angle is not exactly given to us. So if you want to look at the angle given to us is the angle between sort of the tail of this vector and the surface, and that's 30 degrees. But we don't actually, that's actually this angle, and we need the angle between N and E, right? So the E dot A angle, and that means we need this angle. So if we're looking at this, that means this angle, so just sort of drawing this over here. Here's your surface from the side, okay? That's our plane. We have a normal vector pointing up like this, and then if we draw this electric field vector, oops, let me draw it better. It looks something like this. Okay, this is our electric field. And so it's going through the surface, and we're given this angle as 30 degrees, meaning that this angle is also 30 degrees because geometry, and then you have this angle, which should be 90. Okay, so the total angle that we're looking for is 90 plus 30, which is 120 degrees. So our theta should be 120 degrees. And this is just the math way of doing it. So we want to write this as flux is equal to E, which is 180 newtons per coulomb, times 0.15 meters squared, times cosine of 120 degrees. So this, when you plug all that stuff in, should give you negative 2.03 Newton meters squared over coulombs. And the thing I want you to sort of check on this, and this is the electric, this is the electric flux. The thing that's really important here is this negative. And the reason we know it's negative for just by looking at this is because we know if the normal vector points this way, that means the surface is this way and the field is going in through the surface. So we're expecting to get a negative answer. The other way to do this is you could write this as, the cosine of 60. You could do this as the cosine of 60. You could use this angle, 60, and get cosine of 60, which would give you positive 2.03, because that's still the angle between sort of a normal vector and the electric field. 30 is not the angle between any kind of normal vector and the electric field. It's the angle between the plane and the electric field. So you can't use 30. You have to use 60, but that would give you a positive, and then you just have to know it's negative from looking at the problem. So those are both ways you could solve it. But the key is we know the flux is going in, so it has to be negative, and we can figure out the angle from geometry.